Alrighty, so week 10 is where we're at, and we are going to be talking about recursion. We already covered all the different all the different types of lists, the linked list, the circular list, double linked list, and now we're going to talk a little bit about recursion, because recursion is necessary for us to go through these trees that are going to be coming up next week. So recursion is not the only way to go through the trees, but it just makes things a little bit shorter. I don't know if it's necessarily easier. So for extra reference, read chapter 2 and 5 of Carano, and read LaForce data structures. He's got a couple of chapters in recursion. So let's have a look at it. What I have, right? Again, the same two books. And what is recursion? Recursion is a way for a function to call itself a bunch of times repeatedly, similarly to, I don't want PyCharm, cancel, I want C-line. So recursion is another way to make something repeat a bunch of times. We did this in our CSIS45, but I'm going to do it again. All right, so first of all, let's look at actually what I was showing to the CSIS45 class and use what's useful. Okay, so first of all, there's a couple of ways to repeat something a bunch of times. So let's say, for example, I wanted to show the value of I change from 0 to 3 or 0 to 2. What we can do is we can write a loop, and let me just get to where this is. This is that. Okay, there we go. So two ways to do this. So first way is you can do a loop. Right, here's your loop, and that's going to change the value of I from 0 to 2. Right, and there's another way to do it is with a while loop, which is basically going to do the same exact thing. And I'm going to run the program so that you can see it, that there it is, right? I changes from 0 to 2 using a while loop, using a for loop. And there is, well, of course, there's also a do while loop, but it's basically the same thing as a while. But there's another way to do this, and that is using recursion. So what is recursion? I'll show you in a second. Let me erase these two real quick and get rid of all my other examples. Okay, so instead of using a loop, what I can do is I can create a function. I'll call it recursive, which is going to call itself a bunch of times. And the way it will work is it will keep calling itself until some kind of a final condition is met. Okay, so if I was to just call the function the way it is right now, I'll put it right here, recursive num, and if I run it, there's recursive num is just equal to 0. Okay, but what I can do is I can also tell it, okay, well, inside of the function itself, I can say recursive, and I can tell it to call itself with num plus 1. And if I did this, you're basically creating an infinite loop. Just like if I had I is equal to 0 while I is true, and this thing is going to go on forever. Similarly, this here is going to go on forever. We're going to call it with a 0 first. We're going to send the 0. We're going to show the 0. Then we're going to call itself with a 0 plus 1. Then we're going to show the 1. We're going to call itself with 1 plus 1, etc., etc., etc. So if I run this thing, you're going to see that, let's have a look at it, and it actually stops, but unlike my previous programs that I had, if you notice, this one it's exited with a code of 11. Okay, so what is code 11? Well, it's not a 0. Normally when you run the program, it tells you process finished with exit code 0. Exit code 0 indicates the thumbs up, program exited successfully. And if I add a recursive call in there, you're going to see exit code 11. So 0 isn't 11 because the program did not exit successfully. There's some kind of an issue. And the issue is, if you noticed, this thing called itself, I don't know how many times, 174,684 times, okay? And then it stopped. So what's happening is, inside your computer memory or inside of your processor, there's something called a stack. And every time you call a function, you're pushing it on the stack. Every time you return from the function, so if I just call this function one time, right, what's going to happen is we're going to save the memory address of where the function starts, push that on the stack. We're going to go execute the function, and then when the function is done and returns back to where it was called, we're going to pop that thing from the stack. Okay, and you already know what the stack is, right? Stack of plates. So the same structure is exactly what's happening in the CPU. So the reason for this thing to basically run out of spaces, or to not be able to repeat any more than it has right here, is because you can push only so many times on the stack. The stack has a limit. When you push too many things on the stack, eventually it runs out of stack. They call it stack overflow, right? And it stops. The operating system is going to kill it. It's going to say, all right, that's it. You run out of space. You can't call itself. You cannot push any more things on the stack. So that is one issue with recursion. Okay, I can easily make the loop. If I go in there, I can make this loop go to, 3 million if I wanted to. Okay, I'm not going to run it, but the program is the thing is really going to happen many more times than I can do a recursion. So the recursion as a way of repeating something is limited. You cannot do it as many times as a loop. Also, by nature of how a recursion is done, because you have to push something on the stack and you have to pop it off the stack, it is actually slower than your regular loop. So you can't repeat things as many times as you want, or as you would with a loop. It is slower than a loop, but it actually sometimes is more useful for you to do it this way than using a regular loop. Okay, and when we get to the trees, I don't have it in here, but there's some solutions in, if you go to let's say Computer Science Club. Okay, if you look at the Computer Science Club right here on the right, there's a link for internships and work, and among those links, all the way at the bottom, there's this prepare for the interview links, and top 10 algorithms for job interviews. Okay, and in there, it's, there's some basic ones with strings and arrays, and then at some point it gets to like trees. Where are the trees? Tree heap, right? Let's see if I have it. Binary traversal in order, maybe. Yeah. So you can see in here, there's two solutions, and this is Java, but whatever, right? So this is the iterative solution, which requires you to basically create a list, create a stack, and then as you're going through the tree, you have to push on the stack. Push on the stack, and you can see it's pretty long, right? It's not too long, but it is relatively long. But if you wanted to do the same thing with recursion, it simplifies things quite a bit. So the solution becomes a lot shorter, a little bit more elegant. Maybe not the easiest to understand, okay, but it still shows you some of these benefits. And this recursion, I already showed you this. It's maybe I did, maybe I didn't. If you look at Mergesort, okay, the Mergesort is another kind of a sort, which starts with the list and it splits it in halves until there's no more halves left to be split, and then as soon as it's done splitting, then it starts arranging them in the correct order. Okay, so this splitting part is the actual recursive function calling itself with half of the list of things every time until there's nothing left except just one element, and then when it's done, then it starts assembling thing in the correct order, each sublist accordingly. So this kind of a sort is actually faster than all the other sorts that we have learned. Okay, so this one has an n log n compared to all these other ones. The merge sort, the select sort, the insert sort, the bubble sort. They all had a n squared runtime, which was really not that efficient. So this one is a huge improvement. And the way you would do this, the easiest way to do it is using recursion. And you could do it also iteratively, but it's a lot more involved, a lot longer solution, and actually it's more difficult without the recursion. Okay?
Why is this quicker, by the way? It seems like it would take longer.
Because of how many times you call the functions, because of how many times something repeats.
Okay.
Yeah, the actual the repetition. Remember, in one you had a for loop, in all the previous sorts that we've done, you had a loop inside of another loop, and then one happens n times, the other one happens n times, so it happens n squared times. But when you have the recursion, the process is a lot shorter than having to repeat n squared times. So that's why it's faster. So that's why you want to know recursion, and other than this, we're going to use it in trees, so get comfortable with it. So just a quick, now going to the recursion. So I have a recursion. I showed you how it can happen a whole bunch of times. Now what I'm going to do is I'm going to make it happen only 3 times. So how am I going to do this? Well, I'm still going to tell it to call itself, but in here I'm going to tell it call yourself only if my number is less than 2. Okay? And so now when I run this thing, the recursion is right here on the bottom. Right? So it's happened the same exact number of times as the other one. Right? So how does it work? Well, you're calling the function with a 0, right? You're sending a 0, num is equal to 0. You're going to show that 0. Is 0 less than 2? Yes, it is. So now call yourself with 0 plus 1, which is a 1. So imagine going back into that function again, but this time num is equal to 1. We're going to show recursive num equals 1. Is 1 less than 2? Yes, it is. Now call yourself with 1 plus 1. Then goes back. Imagine calling itself this time with a num is equal to 2. Shows the 2, and is 2 less than 2? No, it isn't. And then it stops calling itself. Right?
Is Java, we do the same thing?
Java does the same thing. Python does the same thing. Yeah, recursion is part of pretty much every programming language. Okay? So now, let's say I wanted to do something else. I wanted to grab this thing here, and I'm going to put it right here. Right? So originally, it looked like 0, 1, 2. Now all I did was I just grabbed this thing here, which was originally, in fact, let me just copy this. Copy this. I'm going to throw it right here. Right? And so this was if I had, let me copy this here again. Put it back where it was. All right? So if I have this arrangement of things, right? I have the cout, then I have the if, and underneath it I have that. That produces this result. Okay? So now what I'm going to do is I'm just going to grab this thing here. I'm going to put it down there. And now tell me what's going to be the output.
Is it going to be 210? I don't know.
It will be 210. And yeah, because any other guesses? 1, 2? Okay. So if you actually guessed this correct the first time, means that you remember from what I told you about recursion. Normally people have a very hard time visualizing this because it's hard to imagine how a function calls itself over and over in your head. But let's have a look at it. I'm going to run this thing again, and now you're going to see that it's actually 210. Okay? And now let's see why that happens. So I'm going to grab this thing here, and I'm going to throw it in Excel. Because it's, you remember this, yeah. Yeah, I went over this stuff in the summer, so that's why you know it. And, okay, so let's say I have, this is my function call. I am going to copy this whole thing here. Alright, I'm going to paste it in there. Damn it, I copied again. All right, so this is my recursive call. So what happens is this is my initial call is giving a num is equal to 0 here, right? So num equals 0. Okay? So what's going to happen is it is going to look at this if here. Is 0 less than 2? Yes, it is. So now call yourself with 0 plus 1. Okay, as soon as we do that, I'm going to copy this thing one more time. And I'm going to paste it right here. Okay, so this is my next recursive call. Okay, and we're still calling the same function. I'm just copy pasting it so you can see it easier. And I'm going to draw a little arrow. So we're going from this call to this other call. And orange. Okay. All right, but this time what I'm sending is if this one had a number is equal to 0, then this one is going to be called with 0 plus 1. In other words, this function here is going to receive num is equal to 1. Right? Then it's going to go look at is 1 less than 2, which it is, and we're going to grab this thing and we're going to call it one more time. Okay, so that's the other call. Copy this. Alright, so now we're calling it another time with 1 plus 1, right? Num was 1 for this particular instance of this function, right? 1 plus 1 is a 2, so now the num is equal to 2. Okay, and at this point it's going to look at the if. It's going to say, all right, well 2 isn't less than 2, so and it will stop calling it. Right? So the first thing that it's going to do, right? Now we're finally, after we're done with we cannot do another call, we're finally going to be able to reach to the cout. As soon as we get to the cout, you're going to see the recursive num is equal to whatever, right? Now we're going to see the actual cout recursive num equals, and what value is num here? 2. Okay, and that's what it's going to show. Okay, as soon as it gets to this point, and basically it gets to the yellow bracket on the bottom, at that point it goes back to right where it was called. So it returns from this point back to where it was called, right? Change the color. Go with blue. Okay, so then it returns to the next, right after it was called. So it was called here, so it's going to return immediately after that line, and then it's going to continue down in this particular instance of the function, and it's going to show me the next cout, and the next cout is num is equal to 1, right? So then it shows you the 1, and then at that point, then it's going to go back to where it was called from the previous instance of that function, right? And then the next thing that is going to happen is then it returns at this particular instance of the function, goes down, hits the line cout, and then it shows you the final one, which is the 0. Okay, so that is why it actually shows you this first, then this one, and then that one. Make sense? Any questions? We're good? All right. All right, so for the actual lecture that I have, there's some things in there with triangular numbers. And what are the triangular numbers? Well, there's some examples in here. They're also known as series, right? So let's say you're looking at these squares, right? If you have one column, it's just 1. If you have 2 columns, it's 3. If you have 3 columns, it's 6. 4 columns, it's 10. Right? So you basically keep adding every, it's the sum of each column. Each column increases by 1, and then the triangular number is the sum of all the different columns. Okay? And there's a couple of ways to do it, and that is, well, one is iterative, right? So you can have a total is equal to 0, and then a loop, and then the total is equal to the number, right? And oh yeah, and then this thing depends on the number that is being fed to it. So you can test this thing and you can see that it pretty much works the same way that these triangular numbers work here. Okay, but another example to do this is using a recursion, and the recursion for this is actually a little bit simpler. If you notice, you know, I don't know if it's simpler to understand, but the code at least becomes a little bit shorter. Okay, so it changes from this to actually this, right? Triangle return n plus sum of remaining columns n. Okay, and that's the incomplete version. So that's supposed to be n minus 1. All right, so if you have a hard time visualizing this, the best thing to do is just call this thing, grab the thing, right, and throw it. Right, it's incomplete version. It's incomplete version. Where's the actual complete version? Oh, there you go. So this is the complete version. All right. So there's a base case, which is basically the final, the final condition that happens when the function stops calling itself. That is the base case. So sometimes you might not even have a base case, it's just assumed base case, like that example that I showed you. I didn't have a, basically the base case is when the condition is no longer true, when you can stop calling the function. Okay, so let's have a look at how this would work. So I'm going to grab the triangular number, all right, and I'm going to throw it in Excel again, right in there. Okay, so let's see how this thing is going to work. All right, so let's say we're giving this thing, I'm starting the function with triangle is equal to 4. Okay, maybe not 4, maybe I should do it with 3. Let's see what was 3. Yeah, what the hell, I'll do a 4. Okay, so we're starting this thing with a 4, right? So then we're going to go in there, this first instance of this function. All right, what is the n? N is equal to 4. Is 4 equal to 1? No, it isn't. So that means now call yourself with return here is going to be 4 plus triangle 4 minus 1. Right? So now you have a 3. Right? So I'm just going to go in there and put it maybe at 3. Right? So now it's a 3. So then we can go and get this thing. I'm going to copy it. I'm going to paste it again. Okay, and maybe here. Okay, so now the next thing is, now it's calling itself with a 3, so n is equal to 3, right? Is 3 is equal to 1? No, it isn't. So call yourself, return, this time 3 plus triangle 2. Okay, so that's the next one. And then it's going to go and call itself again. All right, next one. This time the n is equal to 2, right? Is 2 equal to 1? No, it isn't. So call yourself with, now here is we're going to have a return of 2 plus triangle 1. All right? And that's pretty much my last one. Well, actually, we're going to have to jump to it one more time. Copy this, paste it right in there. Okay, so now finally this thing is equal to 1, n is equal to 1, and if n is equal to 1, then we're going to be just returning a 1. So at this point we get to this line, return 1, and now we start coming back. Okay, so when we get to the return 1, now we come back from where we were called, which was right in there. Insert shape. All right. So we're coming back from this line, right back to where we were called, and what we're returning is basically return triangle 1. This piece right here, the triangle 1, is actually going to become what? 2 plus 1. Okay? So that's what it returns. As soon as we get to this return, now we're going to go back to where we were called from the previous one. Alright, so we go back from this return back to this other one here. Alright, so then this time we're going to be returning 3 plus, and instead of triangle 2 here, I can just say 2 plus 1. Right? So you can see it easier, 2 plus 1. Okay, so that's what we're going to be returning here. And then when we get to this line, then we're going to come back. When we get to the actual return, we come back right where we're called, which was here. All right, And then we're going to be returning here. We have a 4 plus triangle 3. Triangle 3 with this was this thing here. So then this final thing is here now, return 4 plus 3 plus 2 plus 1. Okay, and that's your triangular number. Okay, so these are the series. This is one example of recursion, and there's other ones where you can do a multiplication. Basically the same rule kind of applies, instead of doing summation, you can do multiplication, and there's some examples in here for what a recursion is and how efficient it is. And I already explained to you that it's a little bit more time consuming because of how the functions are called and pushed on the stacks, and how you can run out of system stack, and it's slower. You can do it less times, and you can do also factorials. So this is, instead of the triangular numbers where you have a summation, a plus, you're basically just doing the same thing. And here's an example of doing this thing with iteration, with a loop, where basically the total is equal to the previous number times 1. You can do the same thing with a recursion, and the only thing that changes is you're just changing the multiplication, the summation, the plus to a multiplication. Okay? And there's some examples in there of how you can use recursion for creating anagrams, arranging the different letters in different times, in different ways. How you can do it with, this is actually a combination of a loop and a recursion as well at the same time. And I'm not going to go into that too much in detail, but there's a sample program in there for you if you want to type it up. You can do a binary search with recursion, right? So this is your binary search with a loop, which we've had to do already. I think you remember that, right? You're basically guessing the number, higher, lower, and all that stuff. And you can also do it with recursion. This is your recursive call. And the way the recursive call would work is it will call itself, it will call the binary search, it will call itself every time with getting the guess divided by 2. Okay, and this is very similar to how we actually do the merge sort. Okay, so that's another one for you to type up. And yeah, some algorithms lend themselves for a recursive approach, some don't. Again, if you can, and there's an example of the merge sort and the actual efficiency, right? These are your regular sorts that we learned so far, the basic sorts, the bubble sort, the insert sort, the select sort were n squared, and you can see how inefficient they are compared to the the log n one, for example. I don't think the n log n is in there, but that one's more efficient. Okay, yeah. So there's some examples in there for the merge sort, the base condition. Okay, so the way the merge sort is going to work is you're starting with 2 different arrays. So this example right here shows you how to combine 2 different arrays, but in order, right? This one basically checks to see which array. If you have finished with one of the arrays, you can see basically that this array is shorter than the other one. So what you're going to be doing is you're gonna try to see if you have gone through the entire shorter array, and if you have done that, then you no longer need to compare any of the numbers to each other. So what you're going to be doing is you're going to be comparing each of these, so index 0 to index 0. Then you're going to grab the smaller number and you're going to insert this smaller number into a bigger array. So this array C is as big as both of these arrays combined, right? This array has 4 things, this array has 6 things. What we're going to do is we're going to grab the smaller number from each array and then consecutively fill up the array C with those numbers. Okay, so that's what the purpose of this thing here is. Basically, you're going to go through both arrays. You're going to be comparing one array index to another array index, and you're going to be filling up whichever one is smaller is going to go into array C, and then you're going to increase the index of the array that was found to be smaller, with a smaller index, right? So in other words, we look at, let's say we're going to look at 0, right? So A dex is 0 and B dex is 0. Which one is smaller? Well, the B is smaller, right? So if the B is smaller, that means we're going to go into the else, and we're going to say that array C dex, remember C dex is also going to be 0, is equal to array B B dex, which is also going to be 0. But as soon as we make array C0 equal to array B0, we're going to make both array C and array B move to the next index, right? So now when I go through this loop for the second time, I'm actually going to be comparing the second index of array B to the first index of array A. And again, in this case, which one is smaller? It's the 14. We're going to put the 14 inside array C. Array B is going to move to the 39. Okay? When we get to that point, then we're going to be comparing the 39 to the 23. Which one is smaller? It's the 23. We're going to put the 23 inside array C, and we're going to tell array A, okay, now move over to the next index. Then we're going to be comparing the 47 to the 39. Which one was the smaller? The 39 is smaller. We're going to put that inside of the array C, etc., etc., etc. And then when we're done with doing this, not done, but when we're, let's say we get to all the way to the end of most likely array B, right? We have, because why most likely array B? Because 81 and 95 are bigger than anything in array B, right? So that means that we're going to put these numbers in here in array B first, into array C, and then when we're done with that, then we're only left with these two numbers, the 81 and the 95. And by the way, the assumption here is that both of these arrays are partially sorted. That is the assumption of the merge sort. Okay, so after we split everything into smaller and smaller subarrays, we're going to sort them. We're going to sort each of these subarrays in correct order, and then we're going to be merging each of these subarrays into a bigger array in the correct order. Okay? Nice. Okay? So the next one is basically, so whenever we get to, let's say we have emptied up the whole array B, we have put the entire array B into array C, and now we're left with the 81 and the 95, right? So that means that now we're at this while loop right here. So first of all is while A dex is less than size A dex is not less than size A because we have made A dex equal to size A when we emptied the whole array B is already empty, right? So this is not going to be true because the B dex is equal to the size B when we put the entire contents of B into array C. So now we're left with just array A, which are these two numbers, 81 and 95, and this loop basically just puts the 81 and the 95 into array A one at a time. Okay, so that's the idea, but behind the merge sort, and in there I show you the recursive merge sort. Okay, we have a workspace array, which is going to be the one where we're going to be merging these subarrays into, right? And what we're going to do is first we're going to split this thing into the smallest possible arrays for the left piece of this. So imagine a list of numbers. You're going to cut it in half. You're going to call the recursive call a bunch of times until this one basically splits itself into pieces of 2. Okay, same thing with the recursive merge sort on the right. That's going to keep splitting the right piece into halves every time. The part that breaks it down into halves is this right here, right? And then the merge one actually is the one that does what I just showed you. Okay, if it's involved in complicated, it is involved in complicated, so you might have to draw some pictures, otherwise it's hard to visualize. And this is pretty much what I was telling you of how things are, right? So what we're going to do is we're going to be looking at the left, right? If we're looking at the left, we're going to arrange these in two pieces of 2, right? But they're now sorted, right? So this is my first sorted piece, the 21 and the 64. Then I have the 33 and the 70, and then this is the merge part where we're going to be actually merging these things. Okay? And the same thing here. You're going to go in there, the right half of this, we're going to have a 1285. These are already sorted. The 44 and the 3, we're going to sort that subarray first, and then we're going to merge these two subarrays into a bigger array. And then the next step is we're going to put these, each of these is already partially sorted. So this one right here, the 3 is partially sorted, the 6 is partially sorted, and then we repeat that merge process one more time. Okay? And I have more details in there for you. Basically how it works out if it's not exactly in, if you cannot break it out exactly in pieces of 2 and 2, it works pretty much the same way. And efficiency of merge sort is n log n. It's just a matter of how many times something gets copied, and you can look at it through this little table in here based on the number of copies, how many different comparisons you have to do, and that's how we can come up with this n log n relationship. Okay, and maximum and minimum comparisons. So you have the worst case scenario, which is if you have 8 numbers, you would have 7 comparisons, and the best case scenario is 4 comparisons. And of course, you're never going to go with the worst case scenario. You kind of have to average them. Okay, so that's how that efficiency of the merge sort comes up. And the efficiency when the n changes, the maximum comparison, the minimum comparisons, depending on how many numbers are in the array. And I have the entire merge sort in there for you, written out. You have your merge in there. All right, this is your merge, and you have your recursive call, rec merge sort. Right, rec merge sort is basically this whole thing. It just keeps calling itself every time with half and half and half. And then when it's done breaking them into halves, then you pretty much, as soon as and it stops, by the way, this is your base condition. What is the base condition? When the lower bound becomes equal to the upper bound, basically you can't split it any further. That's when you stop doing this, and then you return back and you start splitting the other piece, the upper piece, into halves and halves and halves. And then you do the actual merge sorts that we discussed about in a little bit more detail that I showed you here. Okay? But if you really want to visualize it, you got to draw your own pictures. And that is what I have to tell you about recursion. Now, let me go back to what else I want to tell you in week 10. Recursion, lecture notes. That's the program. Oh, JPEG. Yeah, it's more drawings that I did from previous semester. Okay, so what do you have to do for recursion? I don't think I ask you to do something too crazy. So implement and test the following from the lecture recursion. The merge sort, binary search you already saw, right? Binary search, you do it both iteratively and recursively. Factorial, which is when a function calls itself by multiplying every time what it returns, both ways, iterative and recursive, triangle iterative and recursive, and that's it. Nothing too fancy. Okay? All right, questions? All right, if you have more questions, if you have questions, send them to me. If you want to come to the office hours and draw pictures, I'll be happy to. But again, whenever you're dealing with recursion, it's very hard to visualize. So one of the recommendations are that you're not really supposed to visualize it, right? I know it's hard. I mean, in the beginning, that doesn't make a lot of sense to me, because how are you even going to understand it if you're not visualizing it? So I say, in the very beginning, when you're learning about recursion, it really helps to draw out these little pictures for yourself so that you can see how it works. But then once you get comfortable with recursion, you pretty much kind of assume what's going to happen. You come up with a base case. You imagine what the rest of it's supposed to do. and then just let it run its course. So it's not mandatory for you to kind of, jump 3,000 times in your head to visualize recursion. Okay, so that is all I want to tell you about recursion and week 10. I don't think it's a very hard one, or as far as the assignments are concerned, I pretty much give you most of the answers in the lecture. Oh, never mind, there's one more. Hold on. Edit. Let me add this like little dash in there. So this one is an interesting one. We have, other than these 3 things, which I pretty much give you the answers for these, you just, gotta get it going, gotta get it to work. You have to implement the following method recursively. So what is this method? It is to calculate a compound interest for certain monthly deposits and the actual interest over a certain amount of years. Okay? I actually wrote this to figure out my retirement plan. Yeah, so there's a lot of web pages like the CalSTARS, the state retirement system has like their own formula that tells you, okay, how much money can you contribute every month? All right, this much. All right, and then what interest do you hope to achieve? Okay, this much. Okay, and then it gives you, okay, in 20 years you're gonna have this much money. I said, all right, well, can I write a program for this? Sure you can. You can write it with iteratively, which I give you here, and you can also do it with recursion, which is what you're gonna have to do. Okay? And yeah, there you go. There's different tests in there at the bottom. You can, I guess, maybe play around it, see how long it takes you to become a millionaire, that kind of things. All right. So yeah, that is all you have to do for P10. Okay. Play around with recursion, get comfortable with it, because next week when we get to trees, we're going to be doing recursion again. Questions? Yes. Good. All right. So that's it for today. Go see me in the office if you want to. And I'll see you next week.
I have a question about that Java program. I tried running it yesterday, like by deleting